Okay, let's unpack this. We've got a fascinating deep dive ahead of us today, plunging into the world of hydrocarbon exploration, but with a bit of a twist.
Right.
We're looking at a technology that isn't seismic, which, is often the first thing people think of for finding oil and gas.
The go-to method, usually.
Exactly. Our source material is this detailed presentation from G&G and Matriz about their non-seismic geoelectric method. It's called HRES IP.
And our mission, I suppose, is to get beyond just the technical jargon in the presentation. We want to figure out what makes this HRES IP thing tick.
Yeah, how does it actually work down there, and why is it valuable? Especially, it seems, when things get tricky geologically.
Precisely. Because it's not always straightforward.
No kidding.
Yeah.
And here's where it gets really interesting. This isn't about bouncing sound waves off rocks.
Nope.
We're talking about using electricity and magnetism to see beneath the surface. It's a completely different way of looking.
A different perspective, offering potentially different information than seismic, which can be crucial.
Absolutely. Especially for catching things seismic might miss. Let's dive in and see what this is all about.
Okay, so HRES IP. At its core, it's a non-seismic geophysical method.
Right, not seismic.
It falls under the geoelectric category, meaning it uses the electrical properties of the Earth to figure things out.
And G&G and Matriz, they're the folks behind it.
Yes, they developed and operate this specific HRES IP technology.
All right, so no sound waves, we're using electricity. How does that actually work? What's the basic physics behind HRS-IP?
Okay, fundamentally, it measures two main things: induced polarization IP for short, and resistivity.
Resistivity, okay, that sounds familiar, like how much something resists electrical current.
Exactly that, like electrical resistance, but for rocks and earth materials. IP, induced polarization, is a bit more involved.
Oh, yeah.
It's an effect where even after you turn off the current you've put into the ground, some materials kind of hang on to a charge for a tiny moment, like a very weak, short-lived battery.
Huh.
The source material mentions that things like metallic minerals do this, but non-metallic ones generally don't show much of this lingering effect.
Okay, so you zap the ground, and then you listen for this electrical echo or ringing.
That's not a bad analogy, actually.
Yeah.
The key measurement for this IP part in HRES IP is the phase difference.
Phase difference.
You send out an electrical signal, like an AC current, at a specific frequency. Then you measure the signal you receive back. If there's polarization happening underground, that received signal will be slightly delayed or shifted in phase compared to the signal you sent out.
Ah, so the timing is slightly off.
Exactly. That time lag, that phase shift, is what you measure very precisely. And alongside that, the system is constantly measuring the resistivity too. So you get both measurements together.
Got it. Phase difference for the IP effect and resistivity. But
Yeah.
How does that point you to oil and gas? Hydrocarbons aren't exactly conductive, are they?
No, they're typically highly resistive. But this is where the principle of the reservoir anomaly comes in. It's a really key concept from the source.
Reservoir anomaly.
Okay.
It turns out that at the boundary, the interface between oil and water in a reservoir, or between the oil and the solid rock surface, something electrically interesting happens.
Like what?
You get what's called an electric bilayer forming right at that contact.
An electric bilayer. Like
Yeah.
a tiny charged layer at the edge.
Exactly, a very thin zone with separated charges. And this charged boundary, this bilayer, it generates a measurable induced polarization phase difference anomaly.
Whoa, okay, so the edge of the oil accumulation lights up with this specific IP phase signal.
That's the idea. It's the interface that's electrically active in this particular way, causing that characteristic phase shift. You're not necessarily seeing the oil directly with the IP phase, but rather the electrically active boundaries associated with it.
That's really specific. Fascinating.
And then complementing that, you also usually get a resistivity anomaly. Because as you said, oil and gas are much, much more resistive electrically than the salty water usually found in the surrounding rocks.
Right, so high resistance points towards hydrocarbons too. Correct. So HRESIP is essentially looking for this dual signature. The specific IP phase anomaly indicating the boundary, and the high resistivity zone indicating the potential bulk of the hydrocarbon accumulation.
That makes a lot more sense. You're looking for that specific electrical fingerprint saying, hey, something unusual, possibly oil or gas, is happening at this boundary. Okay, so to capture these pretty subtle signals from deep down, what kind of gear do you need out in the field?
Well, you need some serious kit. First, you need a powerful source to inject enough current into the ground to get a measurable signal back from depth. The source mentions a hefty diesel generator like 125 kVA.
Okay, serious power.
Then you need very, very sensitive receivers. They talk about a 24-channel receiver, the AG-XXL, capable of picking up incredibly small voltage differences down to microvolts over a decent frequency range.
Powerful injection, super sensitive listening. How do you actually connect to the Earth?
For the electrical part, you use specialized electrodes. The source mentions brass ones, specific composition, hammered into the ground. And for the magnetic component, you use these large magnetic measuring loops, coils of wire laid out on the surface, sometimes quite large, like 25 by 25 meters.
Okay, generator, receivers, electrodes, loops, got the gear.
Hmm.
What does it look like deploying this for a big exploration project? How's the field work done?
The main approach described is a surface electric survey using a fixed source.
Fixed source, meaning you don't move the injection point around much.
Exactly. You set up your current injection line in one place, often quite long, and then you deploy a whole array of receiver channels spread out over the area you want to investigate.
What's the benefit of doing it that way, with a fixed source?
Well, the source really highlights this. It allows for simultaneous measurements across all those receiver channels from that single source setup.
Yeah.
This gives you a really high-density network of data points very efficiently. It boosts productivity significantly compared to methods where you have to constantly move the source,
Yeah.
and it leads to more detailed and likely more accurate results.
So cover more ground, faster, and maybe better data. Makes sense. I also saw something mentioned about using wells, an IP well survey.
Yes, that's a neat complementary technique. You can actually lower a vertical line of electrodes, the source line, down an existing well bore.
Inside the well.
Inside the well. This lets you measure the electrical properties from the well outwards into the surrounding rock formations.
I can see how that would be useful.
Hugely useful, yeah.
Yeah.
You combine that with the surface data, and it really helps pin down the exact depth and shape of the oil-water contact, or differentiate between stacks, pay zones, different layers holding hydrocarbons.
That sounds like a great way to tie the surface geophysics directly to known geology from the well. Can you do this fieldwork pretty much anywhere, like rugged terrain or bad weather?
According to the presentation, yes. The system is apparently designed to be pretty robust. They say it works in difficult climates and even in areas with a lot of industrial noise, which can often mess up sensitive geophysical measurements.
That flexibility is a big plus, I'd imagine. What does a typical field layout look like? You mentioned the source line. I recall seeing a diagram from a project in Iran, Dadasht.
Right, those diagrams show a typical setup. You might have a source line stretching, say, 10 or 13 kilometers.
Wow, long line.
Yeah, and then you'd have receiver lines laid out perpendicular to that source line, where you place your electrodes. The distance from the source to the receivers, the offset, might range from maybe 5 kilometers out to 15 kilometers or more, depending on the target depth.
And covering how much area per setup?
They mentioned being able to survey something like 14 square kilometers in a day with one setup, which is pretty decent coverage.
Covering that much ground with all that gear must take a fair-sized crew.
Absolutely. The source breaks down the crew structure. You typically have separate teams. A source crew managing the generator and injection, and a receiver crew deploying and managing the sensors and recording units. Plus, you need accurate GPS teams for positioning everything.
Lots of moving parts.
Definitely. And G&G and Matrice emphasize their personnel strength, mentioning they have numerous experienced geologists and geophysicists, including quite a few PhDs, capable of running multiple 3D HRES IP surveys at the same time, even in tough terrain. That expertise is vital, not just for getting the data, but for processing it correctly, too.
Right. Processing. Let's talk about that. Once you've collected potentially huge amounts of this raw electrical data from the field, how do you transform that into something usable, something that actually points to oil?
That's a critical stage. Involves quite a bit of sophisticated processing. It starts with the basics. Checking data quality, looking at noise levels, making sure all the signals from those dozens or hundreds of receiver channels are properly time synchronized.
Noise must be a constant battle, measuring tiny signals like that.
Oh, absolutely. The source mentions different kinds, general random noise, but also specific things like the 50 hertz hum from power grids if you're near civilization.
Great. The bane of electrical measurements.
Exactly. Wind noise moving the sensors, noise from roads, even people walking near the equipment. A big part of the processing is using clever techniques like stacking, averaging multiple readings, and filtering to suppress all that unwanted noise.
Can they really clean it up effectively?
They show examples, actually, contrasting a bad record full of noise, especially that 50 hertz hum, with a healthy record after filtering. It shows the processing can be quite effective at isolating the signal you actually want.
Okay, so step one, clean the signal. Then what?
Then you get into the modeling and interpretation side of things. This involves building models of the subsurface based on the data and performing what's called inverse modeling.
Inverse modeling. Sounds complex. What's the simple version?
Okay, think of it like this. You've measured the effect on the surface, the electrical responses your receivers picked up. Inverse modeling is the mathematical process of working backwards from those measured effects to figure out the most likely cause underground.
Ah, okay. Finding the underground electrical properties that must have created the signals you measured.
Exactly. What distribution of resistivity and IP properties down there would produce the data you recorded up here? The source mentions doing this often in the frequency domain, analyzing how the signals behave at different frequencies.
Okay, inferring the subsurface from the surface data. Do you do that in isolation or use other clues?
Oh, it's absolutely crucial to integrate it with other information you have. Any existing seismic data, any geological maps, data from nearby wells, you use all that to constrain the inverse modeling.
Constrain, meaning guide the process.
Yeah, basically set boundaries or starting points based on what you already know. It stops the model from going off into unrealistic territory and makes the final interpretation much more robust. Then you calculate specific parameters, like those dual frequency phases we talked about, which are key indicators.
And the end result of all that number crunching and modeling.
The goal is to extract the anomalous parts of the signal, the deviations from the background response, that highlight potential hydrocarbon zones. There's quality control throughout, of course. The final deliverables are usually things like maps and cross-sections.
Maps showing what exactly?
Maps showing the IP phase parameter anomaly. The source really flags the low-frequency, two-frequency phase anomaly as being directly connected to hydrocarbon deposits. So areas showing increased polarization on that map, those are interpreted as outlining the potential oil contour.
Okay, a map of the electrically active boundary.
Pretty much. And you also get resistivity maps. High resistivity zones could be your porous rock filled with non-conductive oil or gas. And you get geoelectrical cross-sections, like slices through the earth, showing how resistivity changes with depth derived from inverting the resistivity curves. Put together, these maps and sections highlight your potential targets.
It sounds like HRESIP provides a very specific, almost diagnostic electrical signature for these potential reservoir boundaries. So thinking about all this, the physics, the gear, the processing, why would an oil company choose HRESIP, especially when seismic is so established? What are the big selling points?
The source lays out a few key advantages. One is its effectiveness in geologically complex areas where seismic imaging can be, well, challenging.
Like what kind of challenges?
Things like layers of volcanic rock that scatter seismic waves, or areas with lots of faults that break up reflections, or near-surface conditions that make it hard to get good seismic energy into the ground. Carbonates can be tricky for seismic, too.
Okay, so when seismic struggles, HRESIP might shine.
That seems to be a major application area. It's also mentioned being lower cost compared to, say, large 3D seismic surveys or just drilling speculative wells, and it's non-destructive to the surface environment.
So maybe not always a replacement for seismic, but a powerful alternative or addition, especially in those tough spots.
Exactly, or a crucial complementary tool. The case studies they present really drive this home.
Let's dig into those. They mention the West Cuban Trough in Russia. What was the story there?
Right, this is an area with a long history of exploration, some old fields. But the geology is described as really difficult. Oil is in sandstone layers, but they're all chopped up by faults. The layers aren't consistent, and there are these tough clay rocks that seismic waves apparently have trouble penetrating clearly.
Sounds like a headache for exploration.
Definitely. So G&G, starting back in 1996, used a combination approach there, using both 3D seismic and HRESIP together.
An integrated approach. Did it work?
Apparently, yes. The source states that between 1996 and 2005, using this combined strategy, they managed to discover and open up 14 new oil fields in this very challenging area.
14 fields. In a complex, fairly mature region? That's quite something.
It really is. The claim is that the HRES IP data helped them unravel the complex internal structure of the reservoirs, which meant they could figure things out with fewer expensive deep wells.
So less drilling needed to understand the picture.
That's the idea.
Yeah.
Which, of course, reduces the cost and risk and speeds up the process of getting those fields into development.
How did they know their combined seismic and electrical interpretation was right before drilling?
Well, they used the combined data to define the likely oil outlines and predict their reservoir properties. And then, crucially, subsequent drilling confirmed these predictions. The source specifically calls out a couple of wells, numbers 21 and 12, that hit the deposits right where the integrated geophysical work said they'd be.
That's the proof, isn't it? When the drill bit confirms the model, the source also talks about success in Iran. Similar story there.
Yes, similar theme of complex geology making things difficult. They mention work in South Iran, and specifically the Daydash project. The presentation even includes a seismic section from the region that visually shows how jumbled and hard to interpret the structure can be.
So HRES IP helped cut through that complexity.
That's the claim. For instance, in South Iran, they generated those phase, anomaly, and resistivity maps we discussed. Based on analyzing the pattern's specific combinations of resistivity and polarization ratio, they identified two favorable areas for potential hydrocarbons.
And the Dadash project, was that a large survey?
Yeah, that one covered a significant area, 300 square kilometers. They collected a dense grid of data points across that region.
So it seems clear from these examples, HRES IP isn't usually used in a vacuum. Its strength often comes from being combined with other data, right?
Absolutely. The source material stresses this integrated approach again and again. HRES IP data is typically woven together with, well, log data, seismic data, sometimes gravity magnetic data too. There's a workflow diagram showing this clearly.
What does that integration let you do that maybe one method alone couldn't?
By combining the strengths, say seismic for the overall structure, HRES IP for details about fluid contacts and potentially rock properties via electrical signatures, and, well, logs for ground truth at specific points, you build a much richer, more complete model of the subsurface.
More confident picture.
Exactly. It allows for better definition of the reservoir layers, a more accurate assessment of what fluids are present, oil, gas, water, better predictions of reservoir quality, like porosity perhaps, and ultimately much smarter, lower risk decisions about where to place expensive wells.
Is there solid proof of the economic benefit? Does adding HRE IP actually make a big financial difference?
They provide a really striking example from a project in Western Siberia.
Okay.
They detail how applying this integrated technology complex led to identifying significant new oil reserves. The figure mentioned is 4,285,000 tons of oil stocks.
That's a lot of oil. What was the cost?
The cost of the geophysical work, the HRES and associated studies by G&G, was around $4 million US.
Okay, $4 million cost. What was the value of the oil found?
The estimated value of those newly identified reserves was over $1.5 billion.
Wait, hang on. $4 million investment yields $1.5 billion in potential value.
That's the calculation presented. It highlights a massive economic efficiency gain for the client, over $1.5 billion in that case. It's a powerful argument for how finding previously hidden or difficult to image resources can create enormous value.
Wow. That's compelling.
And adding to that, the source also notes that this technology complex, including HRES IP, has received an official recommendation from the Russian Ministry of Natural Resources based on its effectiveness.
A government endorsement on top of those numbers. Okay, so G&G and Matrix clearly have the tech and the experience. What's the scale of their operation? Are they working globally? Who uses this?
They seem to have quite a large operational capacity. The source mentions they can run 3D HRES IP surveys in pretty much any terrain with multiple crews. Simultaneously, the number mentioned is over 12 crews.
So they can handle big projects. Where are they working?
Their operational footprint, listed, includes Russia, Kazakhstan, Mongolia, China, Ukraine, Iran, and Indonesia. Quite widespread.
And they've covered a lot of ground.
Yeah, one figure mentioned is 15,000 running kilometers surveyed and work on 60 distinct oil-bearing targets over some period. And their client list includes some very big names in the oil and gas world.
Haiku.
Major players like Rosneft, Lukoil, Gazprom in Russia, NIOC, the National Iranian Oil Company, CNPC, BGP in China, Pertamina in Indonesia. They also list specific project examples in China, adding up to hundreds of kilometers surveyed in various basins there.
Okay, so they're clearly established and working with major companies across different regions. Let's try and wrap this deep dive up then. We've explored this HRES IP method from G&G and Matrix.
And we've seen it's this quite sophisticated, non-seismic geoelectric approach. It gives unique insights by looking for those subtle induced polarization phase anomalies and resistivity contrasts, especially at the boundaries where hydrocarbons meet water or rock.
Right. And it seems particularly useful in those tricky geological areas where seismic might, struggle to give a clear picture. The case studies from Russia and Iran really showed its potential for finding new reserves or clarifying existing ones.
Definitely. And while it can work on its own, its real power often seems to come from that integration with other data, seismic wells, etc. That builds a more complete subsurface picture, reduces drilling risk, and can lead to some pretty significant